So I'm going to talk to you guys a bit about how to make the materials that are necessary for these nuclear weapons. They are essentially the fuel of these weapons. So, Matt's talked about HEU and plutonium already. So basically, highly enriched uranium is just a form of uranium that has a much higher percentage of uranium-235 than what occurs naturally. And plutonium, as Matt said, is an element that you can produce during a fission reaction, not as a byproduct of the fission, but as a byproduct of the absorption. It's a slightly, fine point. But so these are both two materials that are perfectly suitable for nuclear weapons. And the important point that I want to make here, so uranium obviously occurs in nature. Highly enriched uranium does not. Plutonium does not in any appreciable amount. So if you want to get this material, you have to make it, or you have to steal it, or obtain it some other way. But making it is the way most people have gone. So this is a diagram of a nuclear fuel cycle. So what I want to emphasize here is that essentially outlined in the green boxes, the enrichment and the reprocessing. So these are both processes that are part of a fuel cycle that nations could use for conventional civilian electricity production. Enrichment is necessary if you want to use uranium, UO2 type of fuel. Reprocessing is not. But so the point is that essentially this is difficult to police or sort of decide whether or not it's okay for who it's okay to use these processes. And it's easy for a country like Iran, for example, to say, oh well, we have to enrich. We want to have a nuclear power plant, or lots of nations still reprocess. But so these are part of a fuel cycle that could be used entirely for peaceful purposes, but they are also the only real ways to make these weapons usable materials. So dual use is, yeah.
Is there a difference between the level to which you enrich for energy versus the level you enrich for a weapon?
Right, so that's the key difference with enrichment, is that, so for enrichment, for a reactor purpose, you don't want highly enriched uranium. But as I'll get into in the next couple of slides, it's very similar type of setup to get highly enriched uranium. Does anyone have any questions about this diagram before I
don't know if it's about this diagram, but it may be something you can do later. I understand that both enrichment and reprocessing can be used for energy creation. Mm-hmm. But for some reason I have the feeling that enrichment is a more legitimate approach to electricity creation than reprocessing. That countries say that, let's say they want to reprocess, your BS meter should go up. But I don't really know why.
So so I'll talk about that, but the brief answer is that essentially mining uranium, enriching uranium, and just having what's called an open fuel cycle, where you just go through that whole process once, is much cheaper than reprocessing. Reprocessing is an extremely technically demanding, dangerous setup, and really there's no reason to do it. You don't need to extract the uranium from the spent fuel. It actually creates more waste. So any country that says we're going to reprocess, that's why.
It seems like it's headed toward a bomb as opposed to the more air conditioners.
Right, exactly. So it's not something that, so all the pragmatic reasons, economically, waste, all of those reasons that anyone would consider to maybe change a fuel cycle, reprocessing actually makes all those metrics worse. So that's why.
Any non-nuclear weapon state that's doing either should raise red flags.
Right. Yeah.
Because either of these basically put you a decision away from making nuclear bomb material.
North Korea did reprocessing before enrichment.
Yeah.
But they weren't claiming peaceful purpose, were
they? They claimed it occasionally, but without much conviction.
Without a great conviction.
Yeah. They didn't, for example, didn't bother to add a turbine to the reactor to produce power with.
How conspicuous is reprocessing?
That's a good point.
So it's conspicuous, but it's not conspicuous enough to the point where it's super obvious. Like, you would have to know what you were looking for.
What do you look for?
So, sorry.
We watch the reactor itself and when it is operating, when it's not operating. So when you see estimates about how North Korea, how much material they have, it's literally people looking at satellite images, watching for steam, water churning in the river next to it, water stops churning. And then we do calculations to guess how many days it was in there and then how many days it'll be in the fuel pond. Reprocessing and enrichment facilities, those buildings just look like industrial buildings. They're very hard, they don't give off a lot of signatures. They're hard for us to tell when they're running or not running.
So I want to move on to actual enrichment. So I want to mention too that these slides on enrichment are modified from Matt's slides because he does a really great job in his class. So there are other ways you can do this, but the main way that most countries do for enrichment now is using gas centrifuges. The previous technology was called gaseous diffusion. So this is a really technically challenging process for a lot of reasons. So two that I can think of that are what I would say are the main reasons would be, one, the UF6 gas that you use is extremely toxic. It's, in addition to being radioactive, it's very corrosive. It's not something that you want to be anywhere near. And the centrifuges themselves, I heard someone once describe them as finicky, and I think that's a pretty good term. They have to be very precisely aligned, very precisely arranged. Everything has to be just so, so people have said that, a centrifuge that maybe has been sitting in, a bunch of centrifuges that have been sitting in a warehouse for a while and not used, and dust has been allowed to settle in them or whatever, those won't work anymore. So they're very finicky. And it is a much more efficient technology compared to gaseous diffusion. So gaseous diffusion, you may have heard of like the mile-long buildings that were enrichment facilities. That's what gaseous diffusion is. But for gas centrifuges, you really, it is very easy to be inconspicuous in terms of your building footprint and your electricity footprint. And yeah, the statistic that's often cited is that you can make 1 bomb's worth of HEU per year, and I'm not sure what the mass that is being cited for that is, but that facility could have a footprint both size-wise and electricity-wise of a supermarket. So the way this is done is it's sort of a multi-stage process. So inside the centrifuge, it spins very quickly. You have the uranium hexafluoride gas. And because of a very slight difference in mass between uranium-235 and uranium-238, that will separate so that one isotope goes towards the center of the centrifuge and one isotope goes towards the outside. And then what you have is you can put these units in stages so that as it progresses down the line, you'll have a slightly more enriched in uranium-235 unit, and that keeps going and keeps going and keeps going. You actually put the feed in sort of in the middle, not at the front part, and you'll end up with a enriched stream of uranium, which you can tailor depending on how many stages you have to 3 to 5% uranium-235 or 20 or more percent uranium-235, and then you'll end up with a depleted, what's called a depleted waste, which is mainly uranium-238. So uranium-238, depleted uranium, actually does have a lot of uses within itself. So it's extremely dense. They actually use it as like armor for military vehicles. Most universities and labs that make use of uranium for any purpose are using depleted uranium. So, but it's not useful. So if you want to make highly enriched uranium, which is what you would need for a bomb versus the type of uranium LEU that you would need for just a reactor, the setup, the technology you're using is the same. The only difference is in the number of separation cascades that you have. So for LEU, you might need, 10 stages. But as you can see, for HEU, the same infrastructure exists, right? So you're just adding stages. You've already figured out how to use the centrifuges to begin with. It's not any new technology. You're just making your cascade longer. So this is why with Iran, for example, in the JCPOA, this was a big deal because, you know, they already had the centrifuge technology, and, you know, they've said things like, oh, well, if we back out of this deal, or if someone backs out of the deal, we could make HEU within a week. And that's because that already exists, right? And so you're just adding on. Think of it just like a train that you're adding cars to.
I should say, under the existing deal, they couldn't make enough for a bomb within a week.
Right.
You might be able to start, you know, reconfigure and start.
Not enough of the actual
something
uranium base.
Yeah.
Right. So plutonium production is done with reprocessing. So I said earlier, you know, and Matt mentioned too, other than the Oklo reactors in Africa, which are not on anymore, plutonium doesn't really exist in an appreciable amount in nature. But when you have spent nuclear fuel, which is what I'm showing these pictures of these spent fuel cooling ponds, you literally have pretty much every element in the periodic table in spent fuel because they're created with fission products or they're created by absorption from the neutrons. And so you go from this very homogeneous fuel to a very heterogeneous fuel. And reprocessing is the act of literally just exploiting the differences in chemistry between similar groups of elements to extract the uranium and the plutonium from the rest of that matrix. Any questions before I get into what
So
this
enrichment is a physical process, and reprocessing is a chemical process. You're dissolving the stuff and then separating out stuff from the solution that you've got.
Yeah. Did you have a question? Yeah. And I do want to point out too, so, you know, there are countries that reprocess, but again, like you brought up, this isn't necessary, right? You can keep mining uranium, you can keep enriching uranium. Reprocessing is not a necessary part of the fuel cycle. And enrichment, whether you're doing the enrichment or yourself, or whether you're buying, you know, LEU from another country, like that's a necessary part of having uranium light water reactor, sort of conventional civilian reactor.
Excuse me.
Sorry.
I don't understand the difference in gaseous diffusion in those mile-long buildings and the gas,
The
gas
centrifuges.
centrifuges.
Yeah, so the difference is that diffusion is a process that is happening right now in this room, right? It's air molecules or any gas molecules just moving along in normal pressure ranges, normal temperature ranges. We're not inducing any sort of speed, we're not inducing any sort of current that doesn't exist. And a centrifuge is literally taking that gas and spinning it very quickly. So that's why that process, which would happen on its own with diffusion, is happening in a much smaller area.
There's also,
Yeah.
so there's also, the way that diffusion plants were set up, they would have these giant diffusion barriers, which is basically like a giant coffee filter. If you think about putting coffee through a coffee filter, you want the grounds to get caught and the water to go through, right? So if you have an extremely crappy coffee filter, you're gonna get grounds going through with the water, and you might think, okay, I'll put it through one filter, it's gonna catch some of the grounds, I'll put it through another filter, it's gonna catch a little bit more, and by the time I get to the end, I've got coffee, right? I've got just the liquid. So if you think about that with the gaseous diffusion, what it's doing is forcing the uranium in a gaseous form through a giant barrier, but it only catches a little bit of that U-235 that you want. And so you have to put it through then another filter, and then another filter, and each of those is called a stage. So it goes through one stage, it gets a little bit enriched, another stage, a little bit enriched, and that's why it's these huge buildings, because you have to put a lot of gas through in order to get any appreciable quantity. And the
you
reason
need a
that
lot
it's-
of pumping power to
yeah,
get
you need
the
a lot
gas
of
to go
power,
through
you
the
gotta be
barriers.
forcing that gas through, which is why it has a really big electricity footprint as well.
So
The
during the
difference with
Manhattan Project, we
centrifuges
were
then-
using sort of more or less the amount of electricity that Detroit was using just to run the enrichment.
Yeah, so the difference between that then and what Kate said on the centrifuges is each of those, you know, spinning tubes, which could be, you know, anywhere from the height of, you know, a 3-year-old child to, you know, the top of a 3-story building, depending on what design you have. Each of those is kind of replicating one of those giant stages. It's not exactly 1-to-1, it's not one tube to one stage, but it's basically the same idea where each machine is only doing a little bit, and then it moves on to the next one, and it does a little bit more, and the next one does a little bit more. And so you've kind of compacted all that down through a different process, through rotation, instead of forcing gas through.
So nobody does gaseous diffusion anymore?
Nobody, well,
There's
there are still plants operating, but nobody is starting new programs using
Nobody in
gaseous
their right mind
diffusion.
would build a new one today.
That's right. That's
Yeah.
right. And certainly from a proliferation standpoint, you wouldn't do it because it's extremely obvious. Like, you'd be able to find those really quickly. Sorry to interrupt you.
No, that's great.
And we will have time for questions after the presentations. We'll set aside.
So I'm going to show you guys a diagram of what a typical reprocessing scheme looks like, but I wanted to explain. So this, I'm showing the periodic table, which maybe you took chemistry in high school and remember this. But so these elements are color coded on the table, and the color coding just means that they have chemical similarities. The electrons that Matt was talking about in the light colored elements will behave similarly. So as you can see, uranium and plutonium are at the bottom, and they are both colored purple. So you're exploiting the fact that those elements behave differently than all the other elements that are in spent fuel. So that's how you can make a chemical reaction to extract them. So there are other ways you can do this, but the main way that you reprocess is called the Purex process. It stands for plutonium uranium redox extraction. So essentially what you do is you take the fuel, you dissolve it in acid, and then you have a series of chemical reactions that are designed to exploit those color-coded differences I showed you. And ultimately, you can result in a pure stream of uranium, a pure stream of plutonium, and then you would have the rest of your undesirable elements come off in what's called high-level waste. So you can modify it to make it so that you're actually not separating the uranium and plutonium at the last step. But that's a finer point.
Sorry, this is how you get your plutonium.
This is how you get your
From
plutonium.
spent fuel.
From the spent fuel. We talked about this earlier, but the important points are that what's true. This is the main way to obtain plutonium. You can't obtain plutonium any other way in any other appreciable quantity. What's also true is that it doesn't eliminate any need that you would have to dispose of your spent fuel ultimately. It's also true that this process itself actually creates more waste in terms of volume, and it's actually also more expensive. So the one thing that is certain that would be an output that maybe is desirable is creating the plutonium. And all these other outputs are actually making the situation worse, right? So the US used to do this, obviously, and it is currently done in several countries, but we don't do it anymore. Most of the countries that do it are nuclear weapons states. Japan is the notable exception. And as Matt pointed out with the numbers earlier, the fact that you really only need a few kilograms of plutonium to create a bomb, this is a serious proliferation concern because of that small number, right? And also plutonium, the type of radiation it emits is not the type of radiation that is being emitted from a bomb immediately that would kill you immediately. You can walk around carrying plutonium and be fine. So it's not a deterrent. The radiation itself is not a deterrent. So these facilities have to be, if they exist, highly guarded, like extremely kept up in terms of who has access to these. So it's a huge risk. So versus reprocessing and enrichment. So they are both very technically demanding and they're both very expensive, but you could argue that developing a nuclear reactor is also technically demanding and expensive. So it's within the capabilities of many states, right, to develop the technology and infrastructure to do both of these things. Likely not, it's plausible, but likely not a concern for terrorist groups at this time. What would be a concern, though, is if you had a state that was a known sponsor of terrorism or had some sort of unstable government that had these infrastructures in place. Once they're operating, that's different than developing the technology, right? So Matt mentioned, more HU is needed by weight to build a bomb than plutonium, so that could weigh your option in terms of building a bomb. And then we talked about this already, enrichment is a required component, whether you again, buy the fuel from someone else or enrich it yourself. That's required to build a reactor, and reprocessing isn't. So yeah, Japan has a lot, and reprocessing builds up stockpiles of plutonium, right? And so, Japan has a lot of stockpiles of plutonium. They don't have nuclear weapons, but, that's because they are reprocessing. So states can, in addition to making it themselves, making this technology, they can also try to buy these technologies or their parts of them, the components that you might need. And yet part of the non-proliferation effort is, in addition to, figuring out the spread of who's making this, also like who's selling this, blocking that illicit trade. So that's all I wanted to say, and I want to give Alex the floor.